Right now, as I'm speaking to you, a star just died. And while I say this, another 100,000 just blinked out. Here's the part they never taught us in school. 10 billion years ago, the universe made stars 10 times faster than it does today. The peak is behind us. The decline's already started, and it can't be reversed. If the universe is alive, and there are reasons to think it might be, then this isn't its birth. This isn't its prime. This is its first decade of dying. There's a question most physicists won't touch in polite conversation, not because it's foolish, because it's hard to say out loud without sounding like you've lost your grip on the science. Can a universe die the way a body dies? Not metaphorically, not poetically. Can the structure that contains every galaxy, every star, every atom, including the ones currently arranged into you, break down the way an organism breaks down? For most of the 20th century, the answer was clear. The universe isn't an organism. It's a stage, a backdrop, a container, the thing inside which life happens, not a thing that's itself alive. That answer used to feel solid. Now it's getting slippery, because over the last 20 years, every time we look closely at the universe, we keep finding things that look a lot like biology. The structure of it, the behavior of it, the way it changes over time. I want to show you what we found, and I want you to decide for yourself what it means. In 2020, a paper appeared in Frontiers in Physics. Two authors, Franco Vazza, an astrophysicist who studies the largest structures in the universe, Alberto Faletti, a neurosurgeon who maps the human brain. What they did was so simple it was almost embarrassing. They took the mathematical tools cosmologists use to describe the cosmic web and ran them on slices of human brain tissue. These two systems are separated by 27 orders of magnitude in scale. A neuron in your cerebellum is roughly 10 micrometers across. A filament of the cosmic web spans hundreds of millions of light years. There's no reason, none, for them to look anything alike. But the math came back saying, they do. What Vazza and Faletti measured was the spectral density, the way fluctuations distribute across scales, the way nodes connect, the way clusters form around hubs, the level of self-organization. In both systems, the patterns matched. You have inside your skull an organ that looks like a small piece of the universe, or the universe looks like a piece of you. The math doesn't care which way you look at it. Look, the first thing any living thing does is burn energy to stay alive. The universe does exactly that. Our sun alone converts 600 million tons of hydrogen into helium every single second. 600 million tons of matter, gone, turned into light, heat, the energy that warms this planet and keeps you alive. Now multiply that by the 400 billion stars in our galaxy, then by the 2 trillion galaxies in the observable universe. This isn't poetry. This is the largest furnace that has ever existed. The universe isn't choosing to burn. Gravity squeezes hydrogen until it has nowhere to go. A cell doesn't choose to burn glucose either. Chemistry just forces it. The mechanisms are completely different. The behavior is the same. The next thing a living thing needs is structure. Bones, scaffolding, something to hold the soft tissue against gravity. The universe has this. About 85% of the mass in the universe is something we can't see, can't detect directly, and don't yet understand. We call it dark matter. We know it's there because every galaxy we observe is rotating faster than its visible matter should allow. If only the stars and gas were holding the galaxy together, the outer arms would fly off into space. They don't, because they're held by something invisible. Dark matter is the skeleton of the universe, the bones beneath the skin, the scaffold inside which every visible thing, every star, every planet, every you is held in place. Without it, the universe collapses into chaos. With it, the structure holds. You have a skeleton too. You don't see it, you barely think about it, and yet without it, there's no you. At the center of nearly every galaxy, there's a black hole. Not the small ones, the supermassive kind. Millions, sometimes billions of times the mass of our sun. For decades, we thought they were just there, curiosities, galactic ornaments. We were wrong. A supermassive black hole is something more like a switch. It feeds in violent episodic bursts, pulling in gas and dust, releasing jets of radiation that punch out across the galaxy. When it's quiet, the galaxy makes stars. When it's active, those jets compress some gas and shut down others. The black hole decides, not consciously, not with intent, but in the way a thermostat decides, the way a feedback loop in a living cell decides whether the cell divides or rests or dies. Our own galaxy has one, Sagittarius A star, 4 million times the mass of the Sun. It's mostly quiet at the moment. Mostly. The body of a galaxy isn't a passive thing. There's a switch at the center of it, and it's on. There's something else about living cells worth knowing. They keep their internal chemistry inside a very narrow range. Salt concentration, temperature, voltage across the cell membrane. Each one has to stay just right, or the cell dies. Biologists call this homeostasis. Now look at the universe. The universe doesn't actively maintain anything. The constants are just what they are. They don't adjust. They don't self-correct. But here's what gets me. Those constants are tuned with ridiculous precision. Take the cosmological constant, the number controlling how fast space itself expands. Quantum field theory predicts it should be roughly 10 to the 120 times larger than what we actually measure. Physicists call that the worst theoretical prediction in the history of science. If the value were off, even a hair, galaxies wouldn't form, stars wouldn't ignite, you and I wouldn't be here. A living cell actively maintains its balance. The universe doesn't. It just sits there, suspiciously well, at exactly the values it needs to keep going. And we still don't know why. Now, the hardest one. Living things reproduce. They make more of themselves. The universe, by every observation we have, doesn't. There's exactly one universe we can see. As far as our data extends, that's all there is. But in 1992, theoretical physicist Lee Smolin proposed something he called cosmological natural selection. His idea: when matter collapses past the point of no return, past the event horizon of a black hole, the singularity at the center might not be an end point. It might be a beginning, a new universe born on the other side of that crush, with slightly different physical constants, like a child inheriting a parent's genes with mutations. If Smolin is right, and the if is doing a lot of work in that sentence, then universes that produce many black holes would produce many offspring universes. Over enough iterations, you'd end up with universes whose physics is calibrated to maximize black hole production, which would also, and this is the part that should make the back of your neck cold, be the kind of universe that's good at producing stars, and carbon, and you. We're not the point of the universe. We might just be the side effect of a universe that reproduces by dying. In the last 10 minutes, here's what we've established. The structure of the universe, at the scale of galaxies, looks like the structure of a brain. It metabolizes. It has a skeleton. It has switches at its center that decide whether a galaxy lives or quiets. Its physical constants are tuned with the precision of cellular chemistry, and it may, in the only way universes know how, reproduce. 6 biological behaviors in a system we built our entire physics around assuming was not biological. That's not nothing. But here's the question we haven't asked yet. If the universe is alive, what kills it? 68% of the universe is something we can't explain. We've measured it. We've mapped it. We've, as a scientific community, agreed on what it does. But what it is, where it comes from, why it exists, we have no idea. We call it dark energy. The name's a placeholder. It means we don't know. Here's what it does. It pushes space apart, constantly, quietly, faster and faster. Every cubic centimeter of empty space all across the universe is, for reasons we don't understand, pushing all other space away from it. The universe is expanding. We've known that since the 1920s. But what we discovered in 1998 was that the expansion is accelerating, not slowing down, speeding up, as if something is feeding it, growing the void between galaxies into more void, more emptiness, more separation. I'm not calling dark energy cancer. The mechanisms are nothing alike. But in medicine, there's a word for a process that grows uncontrollably, that spreads, that breaks connections, that tears the structure around it apart as it expands. If you wanted the closest biological analog for what's, right now, slowly pulling the cosmic body apart, that's the word you'd reach for. And a healthy cosmos wouldn't need such a thing at all. The data is settled. This isn't theory. This is observation. The decline isn't in the future. It's already started. 10 billion years ago, at the moment cosmologists call cosmic noon, the universe was producing new stars at the maximum metabolic rate it has ever achieved. We weren't here yet. The planet beneath your feet didn't exist. The atoms now arranged into your body were still inside stars that have since exploded. Since cosmic noon, the universe has been making fewer stars. Every billion years, fewer than the billion before. The rate today is roughly 1/10 of what it was at the peak. This isn't a small effect. This isn't a temporary dip. This is a long, gentle, irreversible decline. We're not heading into a dying universe. We're already inside one. It isn't midnight. It's afternoon. The light is still here. There are still births among the deaths. But the angle of the light has changed, and the long shadow is on the wall. Here's the part I keep returning to. As dark energy pushes, the galaxy clusters that were once connected across the cosmic web are being separated permanently. Once 2 clusters are receding faster than light can bridge them, and accelerating expansion makes that inevitable for everything outside our local group, they can never communicate again. They're in the strictest physical sense, causally disconnected. In roughly 100 billion years, every galaxy outside our local neighborhood will have crossed that horizon. The night sky, for whatever observers might exist then, will be smaller, lonelier. Eventually, observers in our merged Milky Way and Andromeda will look out at a sky that's, for all practical purposes, empty. They won't know there were ever other galaxies. They'll think their island is all there is. Imagine for a second, waking up to find that every other organ in your body had simply left. The cosmic body isn't just slowing down, it's going lonely, and nothing in the laws of physics can pull it back. Cosmologists have narrowed the possibilities. Right now, there are 3 serious candidates for how the universe ends. 3 different deaths. I'll walk you through them and tell you honestly which one the data favors. Path 1. The Big Rip. If dark energy gets stronger over time, what physicists call phantom dark energy, it eventually overcomes every force that holds matter together. First, the galaxies are torn apart. Then solar systems, then planets, then molecules, then atoms, then the components of atoms. Everything ends in a final, instantaneous unbinding. The current data doesn't particularly support phantom dark energy. We probably don't end this way, but we can't yet rule it out. Path 2. The Big Crunch. This was the favorite scenario for most of the 20th century. Gravity eventually overcomes expansion. The universe falls back into itself, a singularity at the end, mirroring the one at the beginning. Given everything we know now, the dark energy, the acceleration, this scenario is almost certainly wrong. The Big Crunch is a beautiful idea now, not a prediction. Path 3. Heat death. The quiet one. The one the data overwhelmingly favors. In heat death, expansion continues forever. The stars exhaust their fuel. The last stars, the slow-burning red dwarfs, flicker out somewhere around 100 trillion years from now. Black holes evaporate over timescales so vast they break our intuition. The largest black holes finally vanish through Hawking radiation around 10 to the power of 100 years from now. After that, nothing. No gradients, no flow, no information exchanged. Just a universe at uniform, near absolute zero temperature, expanding into perfect, lightless stillness. There's no violence in heat death. It's, if anything, peaceful. The way a body going cold is peaceful. The organism doesn't fight. It just stops. The number is 10 to the power of 100, a 1 followed by 100 zeros. Mathematicians call it a googol. Here's the only way I know to make that real. Count every atom in the observable universe, every star, every grain of sand on every beach, every molecule in your body. The total comes out to roughly 10 to the 80. A googol of years is 100 billion trillion times longer than the number of atoms you could ever, in principle, see. The current age of the universe, 13.8 billion years, is by comparison a single heartbeat in a human life. 2 astrophysicists, Fred Adams and Gregory Laughlin, mapped out this entire arc in 1999. They divided cosmic time into 5 eras: the primordial, the stelliferous, the degenerate, the black hole, and the dark. Right now, we're in the second era, the stelliferous era, the age of burning stars. It's the only era we'll ever know. and it's already ending. There's a woman sitting in a hospital waiting room. She isn't crying. She's just waiting. She isn't a specific person. She's everyone who's ever sat in a room and confronted the absence of someone they loved and asked quietly, where did they go? Not where their body went, not where it'll be buried, where they went. The specific arrangement of patterns and memories and motion, the thing we called a person. It's the same question. Where does a universe go? Physics has an answer, or part of one. There's a principle in quantum mechanics called unitarity. What it means, roughly, is that information about the state of a physical system is, in principle, never truly lost. When something happens, the universe records it. Not in a book, not in a memory, in the structure of itself. The atoms of a person scatter. They go on. They become air, soil, other bodies, eventually other stars. The arrangement that was a person is dispersed, but the dispersal itself leaves traces. Every interaction those atoms ever had with every other atom is, in some real physical sense, written into the universe's state. This isn't a spiritual claim. It isn't a claim about identity or soul or anything continuing in a way you'd recognize. It's stranger and quieter than that. It's the claim that you happened. That the fact of you happening can't, even in principle, be erased. The universe doesn't forget. Not because it remembers, just because it can't. If we're anything to the universe, we're cells, tiny, brief, embedded inside the larger body, doing what cells do, burning energy, exchanging matter, replicating patterns. But we do one thing no other cell anywhere we can see has ever done. We know we're here. In 13.8 billion years, matter arranged itself into beings who can look at the universe and ask whether the universe is alive, who can map its anatomy, name its parts, predict its death, and feel something about it. The universe, if you want to put it this way, became aware of itself through us, through this, through right now. The cell, somehow, woke up. Yes, the organism is dying, slowly, across timescales that make the entire history of life on Earth look like a single flash of light. The stars will go out. The black holes will evaporate. The cosmic web will fray and dim. Eventually, in a darkness so complete there are no words for it, the universe will go still. But right now, in this specific, improbable, luminous moment, the universe is alive, and it knows it is, because you know it is. Cells don't mourn the organism. They just live. They divide. They function. They carry information forward for as long as they can. And when they can't anymore, they stop. Quietly. Without drama. Maybe that's exactly what we are. Not the ones who survive the universe. It's witnesses. The universe is dying. And we, for this brief, improbable, luminous moment, are the part of it that gets to know. If you can't put this question down, neither can I. This channel's where I go to try to answer it. Subscribe. It isn't for everyone, but it might be for you.